Welcome to Hydrology, Analyzing and Synthesizing Hydrographs. This is Chapter 8, Lecture 1. I'm Dr. Marty Matlock. This is the fun stuff. Let's get started. As we evaluate water movement across the land, we are now focusing on accumulated flow from runoff as water runs off of various landscapes and into rivers, and how we analyze the rivers. We've reviewed the other abstractions from the landscape, infiltration, evapotranspiration in particular. Water balance for runoff is simple: precipitation minus evapotranspiration minus infiltration minus change in storage. Think of these as buckets that get filled and take away from Q. Everything dies, all water evaporates. Those are some of the foundational rules. Infiltration rate versus rainfall is familiar to you by now. You've seen this slide a half dozen times by Thompson. Hydrology for Water Management. It's an incredibly good book. I'd encourage you to add it to your library. So we know we're looking at runoff as part of that, the amount of rainfall that hits the ground greater than infiltration rate and exceeding depression storage. That's the runoff we're concerned about. We know that infiltration and storage directly impact runoff, especially early in the rainfall event. But as soon as those are saturated, then the rainfall becomes effective rainfall, and that becomes runoff. And runoff is really what we design as hydrologists more than anything else, either to manage it, to minimize it, or in some cases to maximize it. The runoff hydrograph is the primary instrument by which we measure flow rate and cumulative flow from the system. Each discrete effective rainfall creates a runoff event. That is to say, when you have rainfall greater than infiltration and surface storage, you get runoff. That runoff event happens over time. That time variable, if you plot the runoff over time, you get a hydrograph. The volume and energy of these events are characterized by the hydrograph. Peak flow is the highest energy of the system because it represents the most mass per unit time of water on the system. And then the duration and volume give you a sense of velocity ultimately moving through a system. Each storm event hydrograph has the following characteristics. It has a pre-event base flow recession. It's A to B here. A rising limb, B to C, a peak flow at C, some maxima, a falling limb, C to D, then a post-event base flow recession, D to E. Now D is usually larger than B, just because of the way the base flow returns. Because some of this base flow is including interflow from the soil, which is not runoff flow. And so we typically acknowledge that some of the base flow will increase from a runoff event because of interflow. Three types of hydrographs are commonly used. The natural hydrograph is obtained from data. If you happen to have a gauging station right at the site you're managing or nearby, you're in high cotton. You have great opportunities to manage this system and to understand your system with direct information. The synthetic hydrograph is more commonly used because, remember, our typical conditions for systems, we rarely have data at the site we're working. Sometimes we have data away from the site and we have to extrapolate to the site. Sometimes we have no data anywhere and we have to synthesize it. So all those conditions apply here too. So the synthetic hydrograph is obtained by using watershed parameters and storm characteristics to simulate a natural hydrograph. And I separated out unit hydrograph because it's a way to create a synthetic hydrograph or to extrapolate hydrographs within a system. It's a theoretical discharge hydrograph resulting from 1 inch, that's the unit, of direct runoff distributed uniformly across the watershed, resulting from a rainfall of specific duration. So if you have 1 inch across a 20-acre watershed, then you have a 20-acre inch Q runoff event. That's the volume of water in that unit hydrograph. So that's the way we calculate the unit hydrograph volumes. And then let's say you have 3 inches. How would you then synthesize the hydrograph for 3 inches? That's what we do with unit hydrographs. We'll address those in coming chapters. The United States is blessed with some of the best hydrologic data anywhere in the world. We have a cumulative surface flow, that is runoff, in our vast networks of rivers and streams from the United States Geologic Survey, USGS. Their locations are indicated in the website here. They're recorded at 15 to 60 minute intervals, stored on site and transmitted to USGS offices every 1 to 4 hours. Real-time data are provisional, subject to revision because they haven't been reviewed and approved. They have current condition tables and time series data available. So the colored dots on the map are the stream flow conditions as percentiles, which is computed on the period of record for the current day of the year. So you have to have 30 years of record in order to get these percentiles. So the blue dots represent areas where you have greater than 90 percentile flow, and the red dots areas where you have less than 10 percentile flows. And the greens, of course, are in that sort of 25th to 76th percentile, that is average. So think of this as your sort of active flood map. What streams are flooding, which streams are in drought conditions. And you can see for July 12th, Sunday, July 12th, we had high flows in the Northeast, Great Lakes states, and some around the Mississippi River, and then some in the Dakotas and Florida. Seems like always Florida, and our colleagues on the north side of Puerto Rico. As we look at runoff and flow data, we select a state, and we can get the site numbers, which happen to be the 8-digit hydrologic unit codes for the sites. And we can see sites like Whiteman's Creek at Indian Drive at Jonesboro, Arkansas, very specific, or War Eagle Creek at War Eagle, Arkansas, White River at Bull Shoals Dam near Flippin. We also happen to have White River at Elkins, Town Branch at Armstrong Street, Fayetteville, Arkansas, this site. And so we have sites that are uniquely located around the state. Selecting a site gives you access to current and historic data. These monitoring sites are co-funded by USGS and other agencies. As always, the federal government starts something and then stops, and then over time fails to maintain it. And so it's such critical data that what we've seen is that other state agencies and organizations have a significant interest in maintaining these data. Let's just take a look at some of the data. Richland Creek flow and gauge height from January 1 to July 12th of this year, till this week. You can see we have discharge in cubic feet per second and gauge height. Now, gauge height is just simply that in the green. That's how high the water is at the site. And it goes here from 5 feet to 22 feet. We have measured discharges, measured gauge heights, and then we have extrapolated. So these are explicitly measured discharges and gauges. We measure them at the same time throughout the year. And this is a way to calibrate to make sure that these things are calibrated. We set these up, as we'll talk about later, as to do so, but we can see that the calibrations are holding pretty true. Now you can see we have a rainfall event, rainfall event, rainfall event, or at least runoff events caused by rainfall events in the watershed. Oftentimes we get storms in these clusters, so you get a rainy week and you get multiple storms through that week. And so you'll have multiple peaks during a storm event before the water goes back down to base flow. So if I'm looking at this and reading this map, I'm saying base flow starts about here in January and goes all the way to mid-March. This base flow is here. We had a wet early or late winter from mid-January to mid-March, and that's pretty typical for this area. Then a wet spring, and so base flow along from this area it can be seen from low flow here over to the declining limb, and then we have all these events. So a number of storm events occur on this period of record. How are these sites established? USGS sets up these gauges, which are basically floats on a line, and as the floats move up and down in these stilling towers, water comes in, fills up the stilling tower, and the float rises up, and it's recorded in the gauge house, and then it's transmitted by antenna to USGS as it's collected. And we measure these in the stream based upon gauge height. So height is the depth of the stream. And USGS will also then measure with using a current meter stream depth to get a stage flow relationship. And so that stage flow relationship is critical for interpreting and converting height into velocity, flow of water. We see these in many of our rivers around the state, and you'll also often see the control panel for transmitting the data up on the bridge. That's what you're seeing when you see these things. By the way, take a look at how streams are measured at the website from USGS. Many of you may find jobs doing this. It's fascinating work. I love it. It puts you outside. You're in the streams. Take your fishing pole along for lunch. It's incredible work. USGS hydrologists construct a stage discharge curve for each gauge to translate. Notice a gauge is spelled with a U or sometimes not a U. G-A-U-G-E is the European spelling. You see it both ways. I'm American, so I spell it without the U most of the time. To translate stream stage, L, that's into stream flow rate, L cubed per T. Now, this is conceptually not complicated. Again, in deeper streams, they use this floating system, and they can use Doppler radars. They can use these spinning volume meters. So they put this thing out on a pole, and then the faster this spins, just like a bicycle tire velocity meter, the faster it spins, the faster the water is moving. So the number of ways to measure flow velocity. If we know a cross-sectional area, and we get this by surveying it, and we know the height of water, then we have a volume. We have an area. I mean, if we have an area, length times width, L2 or square meters, square feet, and then we have velocity per unit time, then that's L per unit time. Then we end up with area times velocity equals L3 over T, which is volume per unit time. Cubic meters per second, cubic feet per second. This trips up a lot of students, just remembering the basic geometry of the river and the algebra of velocity. Keep that in mind. What makes this tricky is that this thing is changing height all the time. And so, the same, presumably at the same height, the same velocity, you're going to get the same amount of water moving past a point at a period of time. So the stage discharge curve for each gauge is used to translate stage to flow rate. And you notice it's kind of S-shaped because the shape of this thing is dependent upon the shape of the stream channel. In this case, a stage of 3.3 feet equals a discharge of 40 cubic feet per second. And notice that these are both on log normal scales in order to compress the extremes. USGS has a new format for their system, which I don't really like, but there it is. It's a simplified, sort of dumbed down version of their data-rich flow data. But I picked a point, the Illinois River at Savoy, Arkansas, picked from the month of like June 14th through July 12th. So you can see at this particular point, June 20th, we had discharge cubic feet per second of about 74. Here it is. So you don't need to read the graph. It does it for you. You can move back and forth. And that's a nice trick. And you can see we had a discrete runoff event here. And you can see we had some rainfall events coming in early July that resulted in runoff events. You can change the length of date you're looking for. You can slide these up and down the calendar with this slider. You can make it a year long, this a whole year of data. It's a powerful visualization. Go back to the classic page when you're here too and take a look at the other data. And by the way, you can find the information on the watershed too, the flow location. So you can see the upstream basin, its area, its land uses, its characteristics. All of this is available from USGS, as well as the flow line. So you go to the website, you point and click at an Arkansas site. It's usually a HUC8 or some number, code number. Data can be accessed as tab-separated values, TSVs, or comma-separated values, CSVs. for analysis over a selected range of data and then dropped into Excel. Based upon these data are plural, based upon this data set, that's singular, at Osage Creek near Elm Springs, Arkansas, you can see how many rainfall events or effective rainfall events occurred from middle of July, beginning January 1. And by the way, look at this pink line at the bottom. That means these data are still provisional. They haven't been fully reviewed and approved as part of the official record yet, but they will be. So how many are there? I count 27 discrete events. 27 rainfall events in 6 months. Look at the peak flow here. It's almost 10,000 cubic feet per second in this small stream. Now we combine the hydrograph, the rainfall data, with the hydrograph in order to analyze the system. The old way of doing this is to put the hydrograph up on the upper axis, and then the hydrograph on the lower axis, x-axis. I have yet to figure out how to do this. I think there's a way in Excel. If you can figure it out, let me know. But for me, that just seems torturous. So what I recommend we do is just put bar charts for the hydrograph on the x-axis as well, and just have a separate y-axis for rainfall. You have flow on the left axis, y-axis, and that's in L3 over T, or cubic feet per second, or cubic meters per second. And on the y-axis, you could put rainfall depth, so that you would have a y2 axis. So again, we have this point of base flow, which gives us the volume under this curve minus the base flow as the direct runoff. We have peak flow, we have the rising limb. There's a lag time between the peak rainfall event and the center of the peak flow. That's the lag time. You have the recession limb, and then it starts all over again. Another rainfall event, and here we go again. The simple graph tells us a lot about what's happening in that river channel. The first increment of rainfall does not cause an increase in stream flow. You guys, we should be very familiar with that now. So it's intercepted. That's our interpretation. There's no increase. It's raining, but nothing's happening. The volume of rainfall over the catchment area is more than total runoff, so soil moisture must have occurred. The lag time is the time from the beginning of the storm. Actually, it's to the middle of the storm here until peak runoff. And it's the time of concentration for flow in the catchment, T sub C. The volume under the runoff curve is above the baseline level. That's above the baseline level of surface runoff. Base flow is estimated to include interflow as well as storm event, as if the storm event did not have effective rainfall. So pretend that the interflow happened, but there was no effective rainfall. What would that look like? That's what there are several ways to develop that. So the length of the rainfall event duration is the time between the start of the rising limb here and when the flow returns, or start of the next event. That's the storm event over time. There are 3 commonly used methods for separating storm flow from base flow: straight line, fixed base length, and variable slope. The straight line method is, as it indicates, draw a straight line from the point at which the surface runoff begins to the intersection with the recession limb. The method is really useful in ephemeral streams where the base flow is often 0. But to avoid overestimating storm flow, an inclined line is used to connect the beginning point of the surface runoff with the point at which the recession limb of the hydrograph or normal base flow resumes. That is, we make some assumptions that there will be some interflow. I think this is the best method. Now, I will tell you there are other 2 methods because whoever you're working with may require you to use them, but I think that they are, unless you have a specific information, I think they're overly complicating what we know. But here we go. Fixed base length method, where the surface runoff is assumed to end a fixed time in after the hydrographic peak. So we just assume that there's this, that we know how long it's going to last, and at the end, that's when it stops. And then a straight line is used to connect the projection points. So you continue down to the peak flow, you continue your base flow line down, and then go right back up to the flow line where the time period that you defined as the end of the runoff event occurs. These are often standardized in watersheds, but again, if you got that much information, you've got real base flow information. You don't need to project it. So I don't really understand the utility of it, but it's often used. And then even more confusingly, because, you know, again, we can magnify, we can look at separating the storm using the variable slope method, where you take the peak flow and base flow down to the peak flow like we did before, and then it goes up to the inflection point. The inflection point is where the rate of decline of flow becomes positive or changes. So that's the inflection point here. So if you do log Q discharge, from here out it becomes linear. So this is the nonlinear part. And so you draw the line down from the inflection point, and you go from the midpoint to the inflection point up, and then down to where you would otherwise go with the straight line. This just digs into the amount of runoff you're getting, and I think you could adapt this just by moving this is why the straight line method they're showing here really isn't what we normally do. We normally would put the straight line back up here somewhere. They all give you the same volume under the curve. And that's the most important part. How much water ran off during that event. Flow and gauge data are messy because the world is messy and it doesn't care about your convenience. Rarely do you see a single storm with a single peak. For watersheds of any size, the storm will often have multiple peaks associated with multiple storms in different parts of the watershed. And that's fine. We can separate those out with rainfall hydrographs, and we know what the impacts would be. So we often look for that single peak event so that we can analyze it and draw larger conclusions. And that's necessary so that we can extrapolate those conclusions to these larger systems. So sometimes you'll have rainfall in the same watershed, multiple places. We saw this with runoff. And so this is all one storm. That's why the hydrograph is important. Base flow also changes seasonally. This is the Illinois River at Savoy, Arkansas, just west of Fayetteville. You can see during April to July, the spring months, we have a certain flow. During the winter months, that goes down and starts to come back up in October in the wintertime. The runoff hydrograph is a way to calculate total effective rainfall, which is to say total volume of water running off the watershed. All the ways in which that water is directed from runoff are called abstractions. These include infiltration, soil storage, evapotranspiration. Since we can't measure these very easily, we estimate them for a region using the hydrograph. We can also use the phi method in order to calculate direct runoff, R sub D. So R sub D is runoff that's direct. And basically, it's the sum of all the runoff from an increment of rainfall minus phi times the unit of time. So if we have 4-hour rainfall and M is 1 hour, so you sum up all 4 of these for the phi times each hour. Hour 1, and each of these time steps is 1 hour. So that's the key, is the time step here. So M is the number of intervals that contribute to direct runoff. Rm is the rainfall during the interval. Phi is a constant that is an index of the constant rate of abstractions in length over time, inches per hour, millimeters per hour. For time interval, delta T, select the number of intervals M of effective rainfall, R sum M, that contribute to direct rainfall. And then you subtract phi delta T. So let's look at an example of this, because it seems pretty simple, but it will, by going through the example, we'll get to see a lot of different, we'll learn a lot of different things. So we have these data for a storm event on April 4th and April 5th. These are military times, so at 20:30 there was no rainfall, started raining at 2100, which is about 9 p.m. And so you get a little bit of rain, and then by midnight basically the rain had stopped. And then we had flow in the stream that started at base flow 203, 246, 283. Then boy, did it jump up to 828 cubic feet per second. And it returned back down to 394, 303. So let's assume base flow here is about 400 CFS. Why would we say it's 400 CFS? Because really it drops down to 394 after the rainfall, well after the rainfall stops. And so this is that straight line method where we overestimate rainflow a little bit to be conservative. Let's calculate direct runoff hydrograph by subtracting base flow from the incremental value. So we label the increments M that have a flow above base flow. And so we have how many flow above 400? We have this number of flows above 400. So when we do that, we have flow, back up. We have flows above 800. We have 11 of those. So we have M equals 11. So you sum the direct runoff hydrograph units. So we subtract 400 because we said 400 is the base flow from all the direct flows over 400. And we get all the direct runoff hydrograph units. And we come up with a total of 43,550 cubic feet of water from this storm event with a base flow at 400 cubic feet, or 400 cubic feet per second. So let's calculate the V sub D and R sub D. So we know that V sub D equals 43,550. And we're going to multiply that times Q sub N, which is 3,600 seconds per hour times half an hour. So that gives us 7.89 e to the 7 cubic feet of water for each, which is our total volumetric flow, if we look at that in a half-hour increment. As with most of these analyses, the actual analyses are simpler than they seem, but you got to put the work in a spreadsheet, and you got to think about your units, and you got to remember we're talking about physical phenomena. We're not talking about theoretical or conceptual things. This is not that complicated. So keep that in mind as you're getting frustrated. So again, back to the phi method. You sum the direct runoff hydrograph units. We've subtracted 400 from all of the Qs we've observed for those areas above that. And that gives us 43,550 cubic feet of water as direct runoff hydrograph units. Now that happens to be 11 increments, so M equals 11 here. For every every increment, we're looking at a half-hour increment, 2230 to 2300, 2300 to 2330. So delta T equals half an hour. Delta T is half an hour. Now we are measuring half an hour in, and we have units of feet per second. We have to do a unit conversion, so we have to do convert this to. In order to convert this properly, we need to convert this to seconds. So we have 43,500 cubic feet. That's all 11 of these units summed up. That's sigma QN times delta T, which is half an hour, times 33,600 seconds per hour, gives us, all the units now cancel out, and that gives us 7.89 e to the 7 cubic feet as V sub D. Now R sub D equals V sub D divided by the watershed area. So we take 7.89 e to the 7th cubic feet and divide that by how many square feet there are in a mile, and there's 7.03 miles in our watershed, times 580 feet squared per mile square. And so that's how you end up, you multiply this out and you end up with 4.8 inches of rainfall. Because cubic feet divided by squared feet equals feet, and then you have to divide that by 12 to get inches. So we have 4.8 inches. That's our estimate using this of RD, using the simple approach. So direct runoff volume, that's V sub D, is calculated by subtracting Q from the base flow. We solve, which we've done, we solve for phi by iteration with M now. So if we want to get phi into this equation, we've already done a first estimator of R sub D. Now let's solve by iteration with M, because now we're building a phi constant for this watershed. So for M equals 1, we say 4.8 if M equals 1 equals 2.2 minus phi times 5. Phi equals minus 5.2. It's a negative. It's not possible. So if we say M equals 2, that's a 1 hour increment. So 1 is a half-hour increment. Then this is a 1 hour increment. We get negative 0.5. But if we say for M equals 3, we have 1.5 hour increments. Phi equals 0.54 inches per hour. So that means that phi delta T equals 0.27. So if phi delta T equals 0.27, then we go back and we calculate R sub D. And the way we do that is we come in here and we calculate excess rainfall hydrograph. That's how much rain is extra. Find the point where the direct runoff begins, and that's here. That's our first direct D sub time. Subtract the abstraction estimates of phi, which we just did. So remember, we came up with 0.27, so we subtract the rainfall from 0.27 and for the effective rainfall. Direct runoff equals observed stream flow minus base flow. So we have excess rainfall here until here. We have no more excess rainfall because the rainfall is less than our 0.27. That's where it goes negative again, and that's where we end up with this this phi. So we add all of the effective rainfall up, and lo and behold, it's 4.8. Now sometimes it may be 4.74, and your other RD may be 4.8. So now what you have is a phi for this watershed of 0.7. And you can say this watershed, you can calculate now this equation using the phi index, this equation, you can calculate R sub D very easily. Because phi equals 0.27. And so now this gives you incredible power for predicting abstractions. Not complicated, tedious, yes, so is engineering. So let's look at creating the hydrograph. The natural method obtained directly from measurements, synthetic method directed by using watersheds, parameters, and stormwater characteristics, such as the SCS method, and the rational method, then the unit hydrograph method. And we'll also look at the USGS regression line method too. All of these are methods for doing the same thing, but they're different tools for solving the same kind of problems. Some are more appropriate for different tools or problems than others. Some require more data, some require less data. Some are more effective than others. This is where expertise matters. This is where you becoming an expert transforms you from a technician to a professional. Please do look at the information supporting this work. I provided a document on relationships between curve numbers and phi indices by David Chen, which will be relevant for the next lecture, as well as the U.S. Water Science School and the National Engineering Handbook, Chapter 16. You have incredible resources at your fingertips. Use them. Thank you.